The theorem of Pythagoras is a well-known theorem. It's also a very old one. Not only does it bear the name of Pythagoras, an ancient Greek, but it was also known to the ancient Babylonians and to the ancient Egyptians. Most schoolboys, schoolgirls, learn of it as a squared plus b squared equals c squared. But the actual statement of the theorem is more to do with areas. So, let's have a look at the statement of the theorem. The theorem talks about a right-angled triangle. So there we have a right-angled triangle. And we show that with this little mark here. So we have a square in that corner. What the theorem says is that the square on the hypotenuse, now that means we have to identify this side, the hypotenuse. And it's always the longest side in the right-angled triangle, and it's always the one that is opposite to the right angle. So it's this side here which bears the name the hypotenuse. So the theorem then says the square on the hypotenuse. So we have to draw a square on this hypotenuse. So there we've got our square. And it says that the area of that square is equal to the sum of the areas of the squares on the two shorter sides. So these are all squares, all the same, all got right angles in them. This is a square as well. All the sides are equal, got a right angle. And what this says is that this area A plus this area B is equal to that area C. A plus B equals C. Okay, let's have a look at a special case and see if we can see how that actually works. I've got here a single red triangle. It's a very special triangle. This side along the bottom is 1 unit long, and that side along there is 2 units long. So I'm just going to fix it with a little bit of blue tack on there. I'm just going to fix it so that in fact I can draw round it. So there we've drawn round that triangle. Now I want to fix some squares on the sides of this triangle. So there's the square on that side. Now the square on this side is going to look, in fact, just a tiny bit different. It's going to be an assembly of triangles, each one identical to this original triangle. So there's half of it. Now I'm going to put the other half on here. So there's the other bit. And we'll make it up with this bit. Okay. Now, remember what the theorem says. It says that if we take the area of this square and add it to the area of that square, we should get the area of this square on the hypotenuse. Well, let's see how right that is. Each one of these red triangles that I've got here and that I'm putting on is exactly the same as these triangles here. So I can put one on there. That one on there. And now we'll put the square in there. Put that one in there. And then finally we'll put this one in there. And what we can see there is that quite clearly the area of this square is made up of the area of that square plus the area of that square. Okay, if this theorem is true, and certainly it seems to be true for this, and it has been proved that it's true, then how do we get the traditional schoolboy, schoolgirl theorem, a squared plus b squared equals c squared? So, we'll draw our right-angled triangle. We'll put on the squares on the sides. And we'll label these squares A and B and C. And we'll label the lengths of the sides, little a, little b, and little c. And the theorem tells us that if we add together the areas of the squares on the two shorter sides, the result is the area of the square on the longest side of the triangle, the hypotenuse. So a plus b is equal to c. But this is a square, and so its area is a squared. And this is also a square, so its area is b squared. And this is a square, and its area is c squared. And so we have the traditional result. Always, when answering questions on Pythagoras' theorem, make sure that you read the question. Don't just write down this result willy-nilly. Make sure you've actually read the question and that you're thinking about which sides are which. Let's have a look at one or two examples then. First of all, let's take a triangle whose two shorter sides are of length 3 and of length 4. And the question is, how long is the longest side, the hypotenuse? So we can label our sides. Let's call this one A, and we'll call this one B, and then the one we want to find is C. So using the theorem, we know that a squared plus b squared is c squared. A is 3, 3 squared plus b is 4, 4 squared equals c squared. 3 squared is 9, and 4 squared is 16, equals c squared, and so 25 is equal to c squared, and so we now need to take the square root of both sides, and so 5 is equal to c. And that's the length of the hypotenuse, the longest side of the triangle. Let's take another example, this time one where we know the hypotenuse. Let's say it's of length 13, and we know one of the shorter sides. Let's say that's of length 5. What we want to know is what's the other shorter side. Let's label these. If I call this one x, let's say, and this one y, and call this one z. Because I've labelled them differently, it doesn't make the relationship any different. It's still x squared plus y squared equals z squared. The sum of the squares on the two shorter sides is equal to the square on the hypotenuse. Let's substitute in now. X is 5, so that's 5 squared, plus y squared, that's what we're trying to find, is equal to z squared. And z is 13, so that's 13 squared. So 25 plus y squared is equal to 169. And so y squared must be equal to 144. And now if we just turn over the page and take that last line again, y squared is equal to 144. We need to take the square root of both sides, so y must be the square root of 144. 12. We'll do one more. Let's take our right-angled triangle here, like this. And let's say this is 17, and this is 15, and this one is the one that we want to know. Now, it's still a right-angled triangle. The hypotenuse is still the side that is opposite to the right angle, still the longest side in the triangle. Let's label our sides. And again, the labelling's different, but the relationship remains the same. P squared plus Q squared is equal to R squared. So let's substitute in our numbers. P squared, that's 15 squared. Q is what we're trying to find, so plus Q squared is equal to R squared, and R is 17. So we have 17 squared. Now we need some numbers. Q squared equals 15 squared. That's 225. And 17 squared is 289. You can work these two out on a calculator, or you can use long multiplication. Doesn't matter which. Now let's find Q squared. That's equal to 289 take away 225, which is 64. And so taking the square roots again, Q is equal to 8. In each of these three, the answers have been exact. They've been whole number values. And these whole number triples, or Pythagorean triples as we call them, occur quite frequently. But you probably won't be lucky when you do questions in getting an exact answer. You almost certainly have to use a calculator for many of them, and you'll have to decide to shorten the answer to a given number of decimal places or a given number of significant figures. I've used whole numbers because it's easier for me to work with them on this page. But do remember, they won't always be exact. In fact, more than likely they won't be exact, and you will have to work them out using a calculator. Let's have a look at another application of Pythagoras. Supposing we know the dimensions of a box. Let's say we know that it's 3 by 4 by 12. So that means we know that it's 3 wide, 4 long, and 12 high. Let's complete our box. So it's 3 by 4 by 12 high. Let's make it look a little bit three-dimensional by putting in a dotted line the bits that we can't see. Question: how big's the diagonal of the box? The diagonal not that runs across a face, but runs from one corner across to another corner. How can we work this out? Well, this is a cuboid. Each of these sides is a rectangle. All the joints are at right angles. Let's put this diagonal in. So there it goes, spanning the box. Well, across here, down to here, and across here, we've got another right-angled triangle. So we know that. If we knew that, we could find that. But this gives us a right-angled triangle down here. And we do know these two sides. So let's see if we can work that out. Let's make clear we've got a right-angled triangle here and one here. So first of all, how long is that? How long is x, the diagonal of this base rectangle here? Well, Pythagoras tells us that 3 squared plus 4 squared is equal to x squared. So that's 9 plus 16 is 25. And that must mean that x is equal to 5. So we've now got x is 5. And we can use Pythagoras again in this triangle. 5 squared plus 12 squared is equal to the length of the diagonal squared. Let's call that y equals y squared. And so we have 25 plus 144 is equal to y squared. So that's 169 is equal to y squared. So y must be the square root of 169, which is 13. So we can use the theorem of Pythagoras in 3 dimensions. We can use it to solve problems that are set up in 3-dimensional objects. What about making use of it in other ways? What about Cartesian geometry? Cartesian geometry is geometry that's set out on a plane that's got Cartesian coordinates, 1, 1, the point 2, 2, and so on. One of the other things about Pythagoras' theorem is this. It tells us, if we have a particular triangle, it tells us the relationship between the sides. And it works in reverse. If the area of the square on the longest side is equal to the area of the squares on the 2 shorter sides of a triangle, then the triangle is right-angled. So this has turned the theorem round. Instead of saying, if the triangle's right-angled, then this is so, what it's saying is, if this is so, then the triangle is right-angled. And we can make use of this in areas like Cartesian coordinate geometry to find out whether or not a triangle is right-angled or not. So, let's take the 3 points, 3, 4, 2, 6, and 1, 0, and let's see if they do give us a right-angled triangle. So first of all, let's plot these points. First of all, we'll mark off on the axes roughly equal spaces. And the same markings on the y-axis, again, roughly equal spaces. And now we'll plot the points. The point 1, 0 will be here. We'll call that the point A. The point B will be the point 2, 6. That will be roughly there. And the point C will be the point 3, 4. And so that will be 3 and 4. That will be roughly there. Let's join up these points to give us a triangle. Now, it doesn't look right-angled, but we don't really know, because these were only rough markings. Is it a right-angled triangle or not? We mustn't believe what our eyes tell us, especially when we can do calculation, which will help us to be exact. So, I need to work out the lengths of these sides of the triangles. So, let me surround this triangle with a rectangle. And because I've surrounded it by a rectangle, these are all right angles here. And I can see now what the lengths of these little bits are. So let me work out AB squared to begin with. AB squared. Now, I can do that because this side here is of length 6. So that's 6 squared plus this length squared here, which is of length 1. So that's 36 plus 1 is 37. And so I've used Pythagoras in this right-angled triangle to find out what AB is, or at least to find out what AB squared is. Let me do that again here, this time for the side BC. BC squared is, and I'm going to use this right-angled triangle here. And again, I can see that this length here is 1, so that's 1 squared, plus the square of this length, so that's 2 squared. That's 1 plus 4 gives me 5. Finally, let's do AC squared. And again, I can see that this length here is of length 4, so that's 4 squared, plus the square of this length here, that's 2 squared, is equal to 16 plus 4, and that gives me 20. Now, if this is a right-angled triangle, if I take the squares of the lengths of the two shorter sides, that's AC and BC, add the squares of those lengths together, I should get the square of the length of the third side, if it's right-angled. And if I don't, then it's not right-angled. So let's do that. AC squared plus BC squared is 5 plus 20. 5 for BC squared, 20 for AC squared. And that gives me 25. But AB squared is 37. That does not equal 37. And therefore, the triangle ABC is not right-angled. The fact that Pythagoras' theorem is about squares is fairly well known. What's not as well known, although it's fairly obvious once you've seen it, is that if you take any regular figure or similar figures and place them on the sides of a right-angled triangle, then the area of the figure on the hypotenuse is equal to the sum of the areas of the same figures on the other two shorter sides. Let's make it perhaps as dramatic as we can, supposing we put semicircles on the sides of this right-angled triangle. Is it the case that the area of the semicircles on the two shorter sides add up to the area of the semicircle on the hypotenuse? Is that so? Well, let's label the sides. Little a, little b, little c, and work out the area. The area of A is, now the area of a semicircle is half the area of the circle, and the area of a circle is pi r squared. Pi times the square of the radius. Now the diameter of the circle is a, so the radius is a over 2. So that's pi times a over 2 squared. And if we work that out, that's pi over 8a squared. A over 2 all squared is a squared over 4. That's where the a squared comes from. And the 2 times by the 4 gives us the 8. B, what's the area of this semicircle here? Well, again, the diameter of this semicircle is b, so the radius is b over 2. So the area is a half pi r squared, and r we just said was b over 2, so we square that, and we have pi over 8 b squared. This one, same again, c equals a half pi r squared, and r is a half the diameter, a half of c over 2, all squared, and so that's pi over 8c squared. So let's add these together, a and b, and see what we get. A is pi over 8 a squared. B is pi over 8 b squared. And there's a common factor here of pi over 8 we can take out, leaving us with a squared plus b squared. But the theorem of Pythagoras tells us that in a right-angled triangle, a squared plus b squared is c squared. And so that's pi over 8 times by c squared, which is just c. And so the question that we asked at the top is true. This does work for semicircles. It would work for equilateral triangles. It would work for hexagons. It would work for similar isosceles triangles, and so on. Pythagoras' theorem is quite a wonderful theorem, and there's quite a lot to be gained from exploring Pythagorean triples such as 3, 4, 5, 5, 12, 13, and the other one that we saw in this lecture, 8, 15, 17.